In the last section, we talked about the most popular explanation for lift. And now I'm going to tell you what's wrong about this theorem. The first thing that is not real is the distance argument. In our most popular explanation, it argues that uh, here air molecules or air particles from the upper surface travels longer distance, so there's lift production. However, if you think deeply into the situation, you'll find that longer distance is not necessary for lift production. It's not necessary. You can simply find some examples as demonstrated here. It's a sail attached to a mast, and it becomes exactly true that in the absence of the mast, then clearly the presence of mass is no consequence in the generation of lift. So you can see the distance on either side of the sail is approximately the same. However, there's always a force acting on the sail as wind blows along the sail. So it tells us that the generation of lift doesn't require different distances around the upper and lower surface. So the first thing wrong about the popular explanation is longer distance is not necessary for lift production. The second thing that is incorrect is the equal time argument. It's something quite weird here. The theorem argues that the air particles get slipped at S and they meet at T. They travel equal amount of time. But if you think deep into it, it is quite wrong. You may ask yourself why it's set at the same time, and you cannot give some obvious explanation, or it cannot be proved. Indeed, in reality, the time they travel is different. And we have the smoke wind tunnel experiment. The smoke particles are injected simultaneously upstream of lifting aerofoil section, generating a line of smoke. And the line of smoke can showcases the movement of the fluid. So what we finally get is the particles moving along the upper surface are clearly ahead of those traveling along the lower surface. So it means they do not travel equal amount of time. Hence, when lift is generated, fluid particles traveling along upper surface reach the trailing edge before those along the lower surface. So it's the second thing wrong about the popular explanation. Equal time, wrong. The third misunderstanding here is about the Bernoulli's equation. Actually, the effect of Bernoulli's equation is often overlooked, and will come with a very similar demonstration as we have done in the first section. We hold a straight piece of paper rather than horizontally. If you blow along one side of the paper, and what you'll get is the paper will not move. It does not experience a force, which seems quite non-intriguing, non-intuitive to our first demonstration, because in the first demonstration the paper will go up, but now it will not move. So there must be some tricky things between the velocity of the air and the pressure, and we are going to talk about it later on. So now we can see that the popular explanation, it sounds quick and logical and seems that it gives a correct answer, but there's quite a lot of misconceptions about why and when will generate lift. And now I will come with an alternative explanation. We'll start with some basic assumptions. If we want to examine the forces acting on a fluid, a partial fluid or a fluid particle, we have to find out the forces acting on it and apply Newton's law of motion. Typically, there are a lot of force acting on the fluid. There's surface tension, there's gravity, there's friction, and there's force due to pressure difference. However, we're going to ignore the surface tension and gravity as well as friction. We are only focusing on the force due to pressure difference. So now the model becomes simple. There's only force due to pressure difference acting on the particle of fluid, and the fluid have to be flowing steadily. I'm going to derive the famous Bernoulli's equations to you. So as you can see here, it's a particle of fluid with cross-sectional area A, which is perpendicular to the streamline. And remember that streamline is the path of a particle in a fluid. The particle is traveling with speed v, and the length of the particle is L. As you can see here, the pressure at the front of the particle is P, and at the other surface of the particle is P plus dP. Applying Newton's second law, F is equal to ma, and acceleration can also be expressed as dv over dt. And there are two expressions for the force acting on the particle. The first one is using Newton's second law, and the second one is using force equal to dP times area. Notice that there's a negative sign here. The negative sign is because the force acting on the particle is in the opposite direction to the velocity of the particle. The mass of the particle can be expressed as L times A times rho, which is mass is equal to volume times density. Volume can be expressed as L times A. So now you can have an equation here. Also, we have to know that dP, which is the change in pressure, is equal to the length times the pressure gradient. The pressure gradient is equal to dP over dx. So now you can have this equation here, and you simplify it, you'll get dP is equal to minus rho v dv. Hence now you can integrate 2 points, arbitrary points along the streamline. We call it 1 and 2 respectively, and you integrate them, and finally you'll get the famous Bernoulli's equation, which is P1 plus half rho v1 squared is equal to P2 plus half rho v2 squared. It's here, the famous Bernoulli equation. So it's very simple math here. You can easily figure out Bernoulli's equation. And there's also one thing to notice is a streamline does not have to be straight. It can be curved. The truth behind a Bernoulli equation, it tells us that if the pressure drops along a streamline in this direction, the velocity increases, and vice versa. So you can see as, for instance, P1, let's say P1 is greater than P2, so it indicates that V1 is smaller than V2, quite straightforward thing. However, the Bernoulli's equation is often overlooked. It only applies along a streamline, here. There's no explicit relationship between P and V of neighboring streamlines. So you cannot apply Bernoulli's equation to different regions. You can only apply it along the same streamline. So now we can explain the quite non-intuitive phenomenon in the two demonstrations we have mentioned. The first one is blowing the paper and it rises. The second one is you blow it here and the paper does not move. So what it means is as you blow above the paper, it's a streamline here. Well, you may argue that the air is traveling faster in this region, so its pressure is lower. Is totally wrong. So what the case is, the air blown out of your lungs is equal to that of the surrounding air. So what really matters is the friction force acting here that stops the air blows out of your lungs. The flow is affected by friction and it brings the flow to rest. So the case here, it is not by Bernoulli because you are looking at streamlines from two different regions. And similarly here, this demonstration matches what we have talked before is Bernoulli's equation can only apply to a single streamline. So the paper doesn't experience a force.